Okay, welcome everyone to my continuation of what is geometric topology. Today I would like to touch a rather sophisticated topic, so the categorification of the Jones polynomial basically, or the categorification of linked polynomials in general. So I would like to talk about knot homology. I'm trying not to define it, so definition is not hard in the end, depending on what kind of knot homology you're looking into, but I just define it kind of a little bit hand wavy. And the point is I would like to replace numbers by vector spaces, and you should think of having a vector space and taking the dimension of that vector space gives you a number, whatever, 5, but this side is way richer. This is the whole space, and this is just a little number. And the reason, well, you will see on the last slide the reason why I would like to address knot homologies, and during the course of this geometric topology I will come back to it actually and fill in some of the details which I'm omitting today. So today, not everything, but kind of morally, I will try to explain it, and it's very similar to the bracket polynomial, and because I would stay with what people call One-Off homology. Okay, so but the main idea, so I will stay with One-Off homology, as I said, but the main idea is the following. You have an honest module, and I write module here because I think of it as having integer coefficients. Later, as you can see here, later I will zoom into the case where I have a vector space. So you can also say a vector space. And that's actually a graded vector space. So you can take graded dimensions as before, and you get a sequence of numbers. And you will see later an example, and you can specialize those sequence of numbers. So you have a grading somewhere, or actually two gradings. It's bi-graded, Q and the T. And you can specialize one of those parameters, and you get the knot polynomial. And that's really the same. So this was here. So One-Off homology is a vector space, if you want, or a sequence of vector spaces, of graded vector spaces. You take the dimension, we get what is called, or what I call, I don't think it has a standardized name, what I call the One-Off polynomial. And if you just specialize the polynomial, it's a polynomial. For t equals -1, you get the Jones polynomial, which I call V here. So V is not, well, not to be confused with my vector space here. In this case, V is just the Jones polynomial. And the story is very similar to taking homology, get rid of the dimensions, or take dimensions, you get what is called the Poincaré polynomial, or the Hilbert Poincaré polynomial. Take t to the -1, and you get the Euler characteristic, kind of this topological nice invariant of any manifold, basically. I'm going to explain Euler characteristic later. For now, this is just the analogy here. If you have seen this, this is really just the same. But the point is, you have an honest vector space, you take dimensions, and then you specialize even further. So in each step downwards, you lose quite a bit of information, and the big thing is actually sitting on top. And what we already like, so Jones polynomial is sitting at the bottom, so this can't be all that bad, and effectively, it's really good. So here is an example what people usually do in topology here. So in the middle slice, so you take homology or cohomology, and you would like to distinguish certain spaces like a circle and a Klein bottle, and homology can do that for you. So you get different associated vector spaces. One of them is Z plus Z, one of them is Z plus Z plus Z mod 2. So they're different. But for example, if you then go to the dimensions, this term dies, and it's just 1 plus t, because everything here is graded. So this is in degree 1. This is, sorry, the other way around. This is in degree 0. This is in degree 1, degree 0, degree 1. And then instead of degree 1, I just write variable t. Instead of degree 0, I write t to the 0. I write t to the 1, and I write t to the I, and so on for degree I. And I just get a polynomial, and that's called the Hilbert Poincaré polynomial. I specialize a polynomial at t equals -1, and I get the Euler characteristic. So let me try to explain that again, and something very similar then it works for One-Off homology and the Jones polynomial. So I have this graded vector spaces, degree 1, degree 0, and degree 1. Okay, and they distinguish. They're invariant, and they distinguish, in this case, the circle from the Klein bottle. If you take dimensions, this term here dies because it's torsion. Let's just say it dies, and the only thing that remains is this part in degree 1, this part in degree 0, and same here, this part in degree 0, this part in degree 1, and I just collect that in a polynomial. So I have dimension 1 in degree 0, and it's t to the 0. That's my coefficient here, and I have dimension 1 in degree 1, and it's 1 times t to the 1, and this is my coefficient here. And what I get is a polynomial in t, and in this case, it's not strong enough anymore to distinguish the the circle from the Klein bottle, but you could specialize it even further, namely t equals -1, and you get the classical invariant, the Euler characteristic of the corresponding space. And these not homologies, whatever that means, so One-Off homology in this lecture, but there's also not Floer homology, and there are many, many, many more homologies, and they categorify linked polynomials like Jones, Alexander, or many, many, many more linked polynomials, and they kind of correspond to this Euler homology to Euler characteristic picture. And kind of fun story. So last time I told you about the Jones polynomial and how the Jones polynomial was a real breakthrough in knot theory in the following sense, actually. Before Jones, there was only one polynomial. It was Alexander polynomial. And afterwards, there were so many polynomials, kind of that the question really changed from how can we find polynomials into how can we order the polynomials, how can we relate them? We just have too many of them. And with homologies were kind of the same. So it started with One-Off homology, categorifying the Jones polynomial. Before there was not a single link homology, and now afterwards they just exploded, and we have so many link homologies, and it just gets a bit crazy. But anyway, this is really, really, really strong and good invariant, and it's defined diagrammatically in this case. So One-Off homology is just doing yoga on the diagrams, and we actually know the yoga already. It's really the same as for, maybe you remember this one, really the same as for the Jones polynomial or the bracket polynomial. I just changed my variables. I don't have an A anymore. I have a Q, but otherwise it's really the same. So we have a normalization. So whenever I have an empty diagram, it should be so no, this was a skein calculus. It should be just 1. And you could pull out a circle. As I said, it's just normalized. And this is now the circle factor. And you have the linear relation among the diagrams, which are normalized slightly differently, as in the last video. So that's not the original definition with A, but a normalization of the definition. So a renormalization of the definition, if you want. Not quite, but basically that's what it is. And the idea is really, really here we have the following. We normalize, we associate the empty knot to 1. We associate the circle to a number. Let me just call this thing a number. Depending what Q is, this actually is a number. If Q is 5, for example, this would be 5 plus 5 inverse. I have no idea what 5 plus 5 inverse is, but it's a number. And the last one is a relation about numbers, basically, because each one spits out the number, whatever A, B, and C, and this is a relation among numbers. So that's that, well, polynomials, if you want. And that's the whole idea of the Kaufman-Skein calculus, and gives you the bracket polynomial. And the main idea is then to just do the same, and you get One-Off homology. So you normalize, and now I switch coefficients to make it just a little bit easier. I go to some vector space. So you normalize here now, every empty knot is normalized to a vector space, let's say a trivial vector space. Instead of pulling out the circle, I pull out a vector space of a certain graded dimension, and the graded dimension is exactly the circle value from the last slide. And instead of having my linear relation in numbers or in polynomials, I have a linear relation in something more complicated, namely I have a linear relation in chain complexes, which I just write down here abstractly, and at one point, not in this video anymore, I will unravel the definition a little bit. But basically, it's really the same. You just now have a linear relation in complexes. In particular, the crucial maps here of complexes, I will come back to them later. For just now, they just exist. And otherwise, it's really the same. It really is the same. So you normalize, you have the circle, which is now, as I said, not a number anymore, but it's a vector space. And you have a relation, but it's now not a relation among numbers. It's a relation about complexes. And what you get out of it is called One-Off homology. And you prove that it's well defined and they're not invariant, and so on and so on and so on. It's pretty good. And the crucial ingredient here are really those maps. And as I said, I will tell you later what it is. And then there's some kind of construction that it takes two complexes, namely this complex and this complex, and generates one complex. But that's a very algebraic and just straightforward construction. And the main ingredient are really those two maps here, which I'm going to cover in a different video because it takes us a little bit further away from knot theory. They come from a slightly different setup, which is related, obviously. Here's a relation, but it's not quite trivial from knot theory itself. It was kind of the breakthrough here anyway. Okay, and then the statement is exactly what you think it is. Up to normalization, it's the same problem with the stupid randomizer one move. There will be some normalization issue. This is a not invariant, but now it takes actually values in chain complexes and no longer in polynomials, which is really this categorified picture. So it's even a little bit stronger because you have values in chain complexes. Oopsala, I can do better. We have values in chain complexes and not in just vector spaces. But if you take homology of this chain complex, then you get what is called One-Off homology, and we have exactly this picture from before. So now we have a bunch of vector spaces sitting in a certain degree, and they're all graded, so everything is bi-graded, and you get a polynomial, the One-Off polynomial, and you can specialize further, and you get the Jones polynomial. Yeah, so that's the whole picture, and I will show you a One-Off polynomial in a second. And what a surprise, it will be the One-Off polynomial of those two guys, because this is kind of the reason why I wanted to end with One-Off homology, because we were struggling for a long time to see actually why they are the same, and or why they're not the same. They're not the same, so why they're not the same. And then the Jones polynomial popped up, and the Jones polynomial solved the problem for us. And for One-Off homology, you can actually do a little bit more. It can detect those knots. So in some sense, are they the same? Strongly no. They are strongly no the same. I will come back to that in a second. But basically, first, what you do is you write down the One-Off polynomial of those guys, and it looks like this, respectively like this. So there's now a t sitting somewhere and the q from before, and setting t equals -1 if I haven't done the correct calculation should recover the polynomials from before up to some stupid scaling, because there might be some different conventions involved. But anyway, so this is just saying what we already know. It's just a more sophisticated polynomial that we have now associated to those two knots. But so they're different, but we already know that. But One-Off homology can do a little bit more. One-Off homology is known to be an unknot detector, for example. That means if One-Off homology, let me just denote it by KH, of some knot is the same as One-Off homology of the unknot, then actually it follows that the knot is the unknot, which is a really strong statement. So it can detect the unknot. So whenever you have a crazy diagram and you're not sure whether it is the unknot, compute One-Off homology, it will give you a yes or no answer, which is pretty good. And you can do something similar for the trefoils. Sadly, you can't, as far as I know, it's not known whether you can detect them as mirror images, but you can detect them as a pair. So whenever One-Off homology tends to spit out of some knot, tends to spit out the One-Off homology of either of them, left or right, you know that your knot is either left or right, which is a really, really strong statement, right? So you can detect trefoils. So we were struggling for a long time to even say anything about those. And now we kind of have the statement that we can even detect them using One-Off homology, which is really, really, really a cool statement in the end. So they're very non-different, and it's kind of very surprising that it took us such a long time. Somehow we had the wrong perspective on the problem. It took us very long time to figure out that they're actually different. Anyway, so as I said, I will fill in some of the details of construction of One-Off homology later, but basically the idea is you take the same rules as for the bracket polynomial and you replace them by categorical versions, like normalization is now a vector space, pulling out circle is now pulling out a vector space, and you tensor it to the rest, and then you have a relation among complexes, which then determines the One-Off homology for you. One-Off homology is really, really strong, so it detects certain types of knots, unknots and trefoil, for example. It detects other knots as well. It's not perfect. There are still knots which are different and have the same One-Off homology, but it comes to be close to be a really, really good invariant. Also from another perspective, because in the end, I haven't showed you how to do it, but it's not much harder, at least in spirit, to compute than the bracket polynomial itself. So it's also very computable. So roughly, we think of it as being of complexity order 2 to the square root of n. I don't think this is proven, but roughly it should be around 2 to the square root of n. And let's say for this video, n is roughly the number of crossings in a projection. So roughly 2 to the square root of crossings in a projection, which is reasonably fast for such a very strong not invariant. Anyway, I hope you enjoyed the video, and I also hope to see you next time.